Okay, so that's the hour. We will get started. This is MSE 498, so if you're not in the class, you're welcome to stay. We have a couple extra machines as long as you're not making too much noise, etc. Okay, so I'll pass around the sign-up sheet. Thank you. Okay, so just a couple of announcements to start today. So some of you may be familiar with this, some of you may not. But Illinois has what's called the CSE program, Computational Science and Engineering. Has anyone heard of this? Okay, so it's a program, it's not a department, which means it sort of draws faculty and students from a bunch of different departments, so folks in aerospace, materials engineering, ECE, chemical engineering. So there's a bunch of different faculty who affiliate with this program, including myself, and a bunch of different students who affiliate with this program. And what's neat is that this program runs all the high-performance computing resources on campus. So the campus cluster, etc., the various GPU clusters are all run by this program. So if you enroll in this program, you get to use those resources, which is cool. And you can also sign up to do a certificate. And so if you scroll down, so cse.illinois.edu, there's an undergrad certificate and a grad student certificate. So if you scroll down the home page, down here you can find out about these two certificate programs. And so basically, if you're interested in doing it's not even quite a minor, it's just a certificate. So you take a couple extra classes, some of which you may already have taken, and you satisfy a bunch of certain requirements. So I think it's pretty light. I think you take 4 classes in computational material science. This counts as one of them. And then along with your degree, when you graduate, you get stapled to it a certificate in computational science and engineering. Similarly, if you're a master's student or a PhD student and you're interested in doing a certificate program, along with your PhD degree comes stapled a computational science and engineering graduate degree. So it's kind of a cool program. There's a lot of benefits. You can apply for scholarships and awards and stuff, get to use some high-performance resources, and indulge your interest in CSE if that's something that you're going to be doing anyway. Perhaps it's a cool thing to do. So if you have any questions, please ask me, but there's a lot of details on the website. And so if that's something that speaks to you, go ahead and do that. It's a nice program. Okay, and then the other thing was, let's just pull up the syllabus and orient ourselves where we are. So going down to the tentative schedule. So we have completed Bash and MATLAB. Last time we went through some lectures on quantum espresso theory and practice, and now on September 16th, we're going to do the walkthrough. So this is the first time we're actually going to run a code together to do some calculations, computational material science and engineering calculations. And following the small length scales to large length scales flow of the course, we're going to start dealing with electrons, so we're going to do DFT. So that's the plan for today, and so this is a hands-on session, so everybody should have the walkthrough and all the ancillary files have all been posted to Compass, and so I'll go through that in just one second, but if you want to get busy downloading those things, if you've not done so already, we're going to need those things today. Okay, so the last announcement was, if you go to Compass, so let me close out this. So if you log into your Compass page and go to your MSE 498 page, in the course content, you will see this document. Oops. MSE 498_software.docx. So that's been up there since the beginning of the course. So that's got instructions on how to install software. So if you have a Linux or Mac in your personal possession that you want to install Quantum Espresso on, it's relatively easy to do, and there are instructions in here for how to do that. If you're using a Windows machine, it's pretty painful, and I wouldn't recommend it. And so if you want your personal installation, you can go ahead and do that. But to save you the pain of all the installation, I've pre-installed all the software on the EWS systems, and so you can use the software directly from the special directory I've set up. And even if you're at home, you can just log in through the SSH and just use that directly. So there's no need to do the installation, but if you want to, I would encourage you to do it. It's not difficult, and it's a nice thing to be able to do. Okay, so before we get started in the walkthrough, are there any questions on any of that? On the DFT theory, on the CSE program, on the syllabus, on the software? Okay, so let's get started. Okay, so if you go to Compass and you go to Quantum Espresso and you go to the walkthrough, there's a bunch of files here. So there is a PDF and a .doc of the walkthrough. And so the PDF is nice because it's portable, And the .doc is nice because you can just highlight code and copy it directly into the bash terminal. If you sort of highlight, copy and paste from a PDF, sometimes it screws stuff up, so doc can be nice for that. But these documents are identical. And then there are 3 files. So there are 2 input files and a bash script. So if you can pull all those down to your desktop, that would be useful, because we're going to actually use them today. Okay. All right, so I have pulled these files down to my desktop. So there's a lot of junk on my desktop, but you should be able to see them here. So there's h2relax.imp, h2sdf.imp, and the run script is down there, the bash script. So I'm using my personal computer, so how am I going to upload these files to the EWS server? What utility could I use to do that? What bash utility could I use? SCP, that's one option, and there's another one that we looked at. SFTP, so Secure File Transfer Protocol. So let me use the second one. So I'm going to do SFTP ALF, which is my username, at ramlnx.ews.illinois.edu. Okay, so I'm going to type in my password. Okay, so if I do ls, that'll tell me what's currently on my desktop. There's a lot of stuff. So let's navigate to my desktop. Present working directory on the remote machine is here. Local present working directory is here. And so let me upload the files. So the command is put h2.sdf.imp. Let's upload that guy. Put h2.relax.imp and put run_ecut.bash. Okay, so all my files are up. So if I do ls, there they all are there. Okay, so let me quit out of this. Okay, so now I'm going to open a secure shell. EWS. Okay, so then I'm just going to put the files on my desktop. Okay, so now I have all my files set up somewhere to go. So if you want to make a mother directory that sort of holds these called Quantum Espresso, because you're going to be doing a bunch of different things and you want to sort of organize your files, that might be a good idea. Or you can just run them directly on your desktop. It's your choice. Okay, so you have those files, and then the other thing you will need, obviously, is the walkthrough. So let me display that. Okay, great. All right, so has everybody got those 3 files and the walkthrough together? Anyone still working on that? Okay, so today we're going to sort of work through this walkthrough together. And so we're just going to run through it line by line, sort of analyze all of the input stuff, all of the output stuff, and make sure everybody can run the code correctly. And this is going to give you sort of the basic hands-on practice that you'll need to do the project next time. Okay, so we're using Quantum Espresso, and so we're using, in particular, the plane wave self-consistent field module, which does exactly what we described last time. It's going to solve DFT using the cone-sham approach. So it's going to compute the cone-sham orbitals. From that, we're going to get the density of the electrons, and we're going to iteratively solve that until we have a converged solution. And once we know the electronic density, we know everything about the system, because then we can compute the energy, all the rest of it. And so we talked about last time how when we actually run Quantum Espresso, we have the executable that takes an input script and spits out an output script. And the input script holds all of the things about the system that Quantum Espresso needs to know. So the configuration of the system, what we're actually studying, plus all of the approximations we want to tell Quantum Espresso to make. So whether we want to use the local density approximation exchange correlation, or a generalized gradient approximation, or the B3LYT, if we want to use pseudopotentials, what we want our K-point sampling to be, what we want our energy cutoff to be. So those are sort of the four main things we said we could monkey with. Exchange correlation, pseudopotentials, and then the energy cutoff and the K-point sampling. And so basically in the input file, there's going to be all that stuff. And so we need to make sure we understand how to communicate that to Quantum Espresso. Okay, so the simplest thing you could possibly study perhaps is the hydrogen atom. We're going to go a little bit more complex and do the hydrogen molecule. And so for folks that may not be super familiar with this, this is 1 proton, 2 protons, and 2 shared electrons. Okay, and so there's going to be a bond length at equilibrium between these protons, and then the electrons are going to start delocalize over these 2 protons, and that's what we want to compute. So we know it's going to look something like this, but we actually have a quantitative answer rather than a terrible drawing on the board. And so we'd like to know the electronic density of the electrons around these 2 protons. So that's what we're going to calculate, and if we know that, we can compute the energy and all these other exciting quantities you may want to know. Okay, so let's run through this slowly, and so if at any point you feel like you're getting lost or you have a question or I say something you don't understand, please do just stick your hand up. So the point of this is to sort of run through this together as a class and make sure we understand everything about the code that we need it to do. Okay, so the first thing is the executable for Quantum Espresso is stored in this rather sort of obscure and long directory name. And so we need to make sure that everybody can run this. And so the way you're actually going to run the code, I don't really want to do that. Is that I'd like you to type this long address or copy and paste this long address into your terminal and just make sure you can run the executable. And so class MSE 498AF software 2_espresso, and then it's actually in the bin, which is sort of where the binaries are located. And the one we're going to be using is pw.x, which is planewave.executable. And so if you type all that junk in and hit enter, you should get something like this pop up. Okay, so is everybody able to get that? Okay, so have you typed the address correctly? So that's always the first thing. If you copied and pasted it, there may be junky characters if you pull it from the PDF. So copy and pasting from the doc file should work. Copy and pasting from the PDF is always a pain. Has everyone managed to get the screen? People still having trouble? Okay, so stick your hand up if you're having trouble. Okay, so let's figure this out. Also talk to your neighbors. If your neighbor has solved it, then that's great. So some peer support. Okay. Yes, absolutely.
Oh, okay. Because if you just type in this, it does not work.
Yes, because that's just a directory, so that's not an executable. That's right.
Okay.
Yeah, I would delete all of that. So there's some junk at the beginning. Yeah. So you can also, once you start typing something, you can hit the tab key, which will auto complete, which can save you some typing.
Oh, wow.
Oh, great. Thank you very much. Okay. Anyone here having difficulties? Yep. So you're still in SFTP. So you don't actually have a secure shell. You're still in sort of copying utility. So you just want to hit quit to quit out of SFTP. Okay, great. So now if you type a string or paste a string. So that's the encompassing directory. So now you need to have /bin/pw.x. Yep. Terrific. Okay. Yep.
How did you get it string profile? I mean, from a SFP?
So we use the put and the get command.
Yeah. So I just didn't find it.
Okay. So that was. Do you remember when we covered this in the lecture?
Yes.
In the bash. So all the commands are up there, and so you can fill up the lecture slides anytime and look for the command. But basically, if you do ls, okay, so let's go to your desktop. Oh. Okay, so your present working directory in the remote machine is your desktop, and your local present working directory is here. But actually, you're already on the remote Linux machine, so you don't actually need to do a secure file transfer. So I was doing it to illustrate how you would get it from a local machine up to this machine.
Okay.
But you're actually sitting here physically, so you don't even need to do it.
Okay.
So you should just quit out of this, and then if you go to your home, yeah, so you can actually just go to Compass and download the files, and then just use the terminal directly. Okay?
Thank you.
Okay, has everyone managed to do that? Okay, so this is just a directory. So you need /bin/pw.x at the end there. Yeah. Okay, so there may be, is there a space at the beginning here? Oh, also you're spelling with an X. That's your problem. So everything is yes, yeah. Yeah, spelling mistakes are a pain in long directory names, as I'm sure you. There we go. Yeah. Okay, terrific. Okay, so as we all found out, it's a big pain to keep writing that whole string. And so does anyone have a suggestion how we might save some time, how we might develop sort of a shortcut to that directory? What could we change in our sort of bash environment? The bash profile, so we could put it in our path, exactly. So let's do that together to save ourselves a lot of pain. So I think I have it in. Okay, so this now is the file that I talked about earlier. It's on Compass. It tells you about how to install all the software. And so at the very beginning, it tells you that, okay, actually I've pre-installed Quantum Espresso for you in this crazy location. It's horrible typing this whole thing, so why don't we add it to our bash path? So you remember how you added things to your path in your bash profile, and so then it allows you to sort of tell bash that anytime I type pw.x, I want you to know that you have to look in this directory and check if it lives there. And so that would allow me to type just pw.x instead of this crazy long string pw.x. So it saves you a lot of time and it saves you lots of spelling mistakes. So let's remember how we do that. And so if you have the screen and you want to quit out, you press Control-C. So Control-C gives bash sort of a break signal. It just says break whatever you're doing, just quit. And so it will break you out of that. And so then we remember we go to our home directory. And we do ls-al to see all our hidden files. And right up the top, we should see our bash profile. And so you remember that we did before, we're going to VI our bash profile. And then we had all these export commands. And so we're going to add one of these export commands to the bottom of our file. And so just go all the way down to the bottom of your bash file. And you want to write a command, line that looks something like this. And so if you add exactly the string, so export space path all caps equals $path colon, and then this crazy big string, that tells bash that it needs to look in this directory whenever you type pw.x, and so you won't have to type all that stuff. So double, triple, quadruple check this string, because if you spell it wrong, it's not going to work. So it needs to be precisely correct. especially found out that Bash is very unforgiving for spelling mistakes. And so this is unfortunate, but you just have to make sure everything is in the right place. So make sure all the underscores are correct, all the letters are correct. Yeah. So when I did VI Bash profile, it opened and created a new file. Did you do VI dot Bash profile? So it's in your home directory. So you need to do cd space tilde, which will take you home, and then do dot Bash profile. So we talked about before that the dot prefacing a file name means it's hidden typically. So it's a system file. So we don't want users typically seeing this file. We only want sort of super users like you guys who are now all Bash experts to be able to use it. Anyone else having difficulty with their Bash profile? Yes. Oh, you were missing it, right? Did you ever create one, or was one ever created? Okay. Yeah. Okay. So let's do. Okay. So let's do ls-al. So ls space, and then dash rather than dot. Yep. And then al. That will show all your hidden files. And so if you go up to the top of that list, let's see what you have. Okay. So there's a bash rc. That would work. Let's go down and see if you have a dot profile file. Okay, so let's modify the bash rc. So let's do vi space dot bash rc. Yep. Yep, that should do it. Yep. Okay, so then you can write your export line in there. Yeah, that's right. So you can do all three if you want at this time, but that's the one you want. Yeah, so a brand new line. Yeah, just copy the whole thing in there. I have no idea, actually. That should be good, yeah.
So we just copy those 3 lines onto the VI Bash profile?
Exactly. Yeah, so just 3 brand new lines in your profile. So right at the bottom. So you're missing /software between AF and 2 Espresso. So yeah, so copy and pasting from the doc file can be a good idea because it sort of prevents these sort of mistakes. Okay, so that should solve it. And then you're just adding export lines. So yeah, it's all the way down to the bottom, and then you can just copy and paste the lines in.
Can you? Because I thought control copy doesn't work on terminal.
I think it should work actually in VI.
Oh, I see. In the VI mode?
Yeah.
Oh, okay.
Very nice. All right, looks good. So has everyone managed to modify their Bash profile with those lines? Anyone else still having difficulties? Okay, so once you have this line in your Bash profile, you're going to want to quit your terminal, so just close the terminal and reopen it. So why do we need to do that? Because the terminal only calls the Bash profile when it first boots. And so your current terminal is not going to know about this line. So you need to close it and reboot it, and then you should be good. So I'm going to quit out of my VI. I'm going to close my terminal. I'm going to reopen it. So once I've done that, I can now just type pw.x, and I get the same thing. So it saves me all that pain. So if you reopen your terminal and type pw.x, your Bash profile now knows exactly where to look for it, and you should get all the same stuff as you got before. So has anyone not got that? Okay. All right, so if your neighbor has got it, talk to them, and I'll come around and try and help you. Okay. Yes, that looks good. Yep, just close that guy. No, it's not signed. Okay, so let's look at your profile. So if you do, and you're modifying your batch profile, that's right. Take a look in there. So class, MSE, software, Espresso. Yeah, that looks good. So why did that copy a doc? Okay, so that works. That's very strange. Okay. Oh, it did? It never worked? Oh, interesting. Okay, but with the same computer it failed? Okay. Let's try and see if we can put it in. You also have a bash RC. We could try putting it in your bash RC. Okay. So I don't know why your bash RC is working, your bash profile isn't, but that's the way it is. So, yeah. Okay. All right. Anyone else having difficulties? Okay, so if people are having problems with this, try and add this line instead of to your bash profile file to your bash RC file. So I don't know why one should work and one should not, but it's exactly the same trick. You just want to go home, and then you want to do vi.bash rc. So before we had vi.bash_profile, now we're going to do .bash rc. So it should look very similar to your bash profile. Just go all the way down to the bottom and paste those lines in. And let's give that a go. So exactly the same thing, just paste in the export path line into there. Yeah, .bash rc. This is just one of those, there are two files that are executed upon booting a terminal, bash profile and .bash rc. I don't know why one should work and one should not, but it seems to be that bash rc is working. So for this particular Linux system, maybe that's the way it works. Yeah. It's installed on sort of a system, a file server that's connected to the EWS server. So it's in /class. Have you searched there? Okay, so let's take a look. Oh, it's a hidden directory, so you need to type the whole thing. Yeah. You need to type 498 AS. Then you can see it. So it's like an auto-mounting directory. So they hide it unless you know where it is. I don't know why they do that. How is that working for people? So modifying bash RT, does that work? Anyone having difficulty still? Okay.
What was it again? Oh, yeah. Okay. So, and then I do, of course, vi .bash RT.
Mm-hmm.
Is this the line, or did I copy and paste from?
It seems to have missed the beginning, so it should be export, yeah. So you can just add that to the beginning.
And this F should not be here.
That F should not be there, that's correct. This is great bash practice, by the way. So,
so here, now, why don't we need to add pw.x? So how does it know that if we do pw.x, they help?
So what you're telling it is, when I type an executable's name, I want you to check and see if it lives in this directory. So you're not providing the executable, you're providing the directory in which it lives. Yeah. So you can actually have multiple executables in there, and Quantum Espresso does have multiple executables in there. So in principle, you could call any one of them now.
Now, so Quantum Espresso already knows that pw.x is already here.
Now Bash knows about it. Yeah. So it didn't before, but now it knows when you type pw.x, it should check in that directory.
Okay.
Excellent. Very good. All right. Anyone else still having sticky problems with this? All right. Very good. So that's going to save you lots of typing. That's excellent. Okay. So let's proceed with our walkthrough. Okay. So good. And then the other important feature is if you get stuck, there is a bunch of documentation that's in a very similar location. Instead of /bin, you have /doc. So you can look up documentation for the code. It's actually easier just to look online. So if you just Google Quantum Espresso, find the Quantum Espresso website, you fill out the documentation. That's simpler. But in principle, you could use the local documentation which has been installed for you in this directory. Okay. If you want to do a local install, like we said before, you should look in those installation instructions I provided you on Compass. And then just one quick reminder, we talked about this before, but Quantum Espresso uses sort of quantum mechanical unit set, and so don't be scared of this. It's just that the units in which Quantum Espresso is written and run are slightly weird. They're not SI units. And so lengths are in bores or atomic units, which is this many angstroms, so you're going to need to do a conversion later on, because you're going to find some answer in bores from Quantum Espresso. I'm going to ask you, what is that in picometers or angstroms or something? So you just look back here and figure it out. Energies are in Rydbergs, which is this equivalence in electron volts. Sometimes we have kilocalories per mole or kilojoules per mole. Quantum Espresso uses Rydbergs, but if you want to go from electron volts to either of these guys, you can do this double conversion. And an electron volt is this many joules. It's a very small quantity of energy. So just a quick reference for you to be able to do changing of units without having to look up on the internet what those things are. Okay, so bottom line is Quantum Espresso's lengths are in bores and its energies are in Rydberg. So let's just remember that. That's all you need. Okay, so let's do this H2 molecule. And so we're sort of going to do two things. And so we're going to first of all guess a bond length for the H2 molecule. So we're going to say, I think the protons are going to be this far apart. Then we're going to compute the energy of that hydrogen molecule. And then we're going to find out if we were right, if we guessed well or we guessed badly. So how are we going to know if we guessed well? So how are we going to know what the equilibrium bond length should be? So we're not allowed to look up any textbooks. We have to compute it using first principles density functional theory. So how are we going to know, at least internally within Quantum Espresso, whether our guess is good or bad? So it can converge. So you can guess a terrible bond length, and you will still be able to converge an energy for it. You will still be able to find the structure of electrons around two protons pinned at these locations. So certainly convergence is a first criterion, but that doesn't answer whether we're really at equilibrium or not. Take derivatives off energy. Excellent, that's right. And so the dumb way of doing that is just to compute for a bunch of different bond lengths and figure out where the energy hits a minimum. But you're absolutely right. The smarter way is to take derivatives. So what's the derivative of an energy with respect to a length? A force, exactly. So what's going to experience a force if your guess is incorrect? Who's the force going to be acting upon? The other guys, the proton. So you're going to compute an electronic structure, and the protons are going to either be happy or sad. If they're sad, they're going to experience a force that's going to want to push them closer together or further apart, depending on how bad your guess was. And so at equilibrium, the force on the ions, on the protons, should be zero, because it's the bottom of this energy well. Does that make sense to everybody? You can think about it in two ways. You can think about it in an energy sort of perspective, that you're trying to find the bottom of this energy well, or you can think about it as the first derivative of energy, which is a force. And so you're trying to find where the force hits zero, and the protons are happy. So if you guess too short, the protons are going to want to move apart. There's going to be a net force pushing them apart. If your guess is too long, the protons are going to be unhappy, and there's going to be a net force pulling them together. So that's exactly what we're going to do in part two. So the first calculation is the first step. We just make a guess and compute an energy. The second part, we're actually going to figure out what the equilibrium bond length is, and then we're going to compare that to experiments and see whether the experimentalists were right. Well, really, we're going to see whether we were right. Okay. Okay, so that's the plan. So this is just what you did before. So you made a directory. You can call it whatever you want. You might want to have a nice structure where you have the course name, you have something called runs, and then you have H2, or you can just do it on the desktop, whatever you care to do. So it's up to you how you organize your runs. Because you're going to be doing multiple runs, you probably want some sort of file organization, but it's unnecessary if you don't care. Okay, so let's actually get into the meat of this. So let's look at the input file. And so we said that the way that we run Quantum Espresso is that we call the executable, so pw.x, and so we're going to, from the bash terminal, call it like this, and so /pw.x. Excuse me, you don't even need that. You can just do pw.x straight up. So pw.x, and then we need to supply some sort of input file, which in our case is going to be h2.scs.inp. And then continuing this line, we dump it to an output file, which is going to be h2.scs.out. And so because you've all nicely modified your bash resource file, your .bashrc, you don't need all the junk out front here. You can just type this directly. Okay, so this is the input. This is the output. And so let's take a look at our input and let's see what we're telling Quantum Espresso to do for us. So let's just open that file in a text editor. Or you can open it using less in the bash terminal, whatever you like. I need to be on the desktop. Okay, so this is my file h2.sdf.imp, just visualized in less. Okay, so let's run through this line by line. So the file looks like this. And so the first block is sort of a control block, and so it's basically telling Quantum Espresso the rudiments of how you want it to run, what calculation you want it to do. The next block is sort of setting up the system, setting up the electrons, and then specifying exactly the names of the ions. So let's go through that slowly, line by line. Okay, so has everybody managed to open that file? They're sort of visualizing that file right now. Okay, so let's step through it. So stick your hand up at any point if something I say doesn't make any sense or you want a little bit more information. Of course, we can always look up the documentation if we want. Okay, so control is the control block, calculation SCS, so it's going to be a self-consistent field calculation, doing exactly what we described in the lectures, solving for the cone-sham orbital self-consistently until we converge. Of course, it's going to be plane waves because Quantum Espresso only uses plane waves. If we wanted to use a Gaussian or a Lorentzian basis set, we would need to use a completely different code altogether. And so, of course, we're restricted to plane waves. Okay, the restart mode from scratch tells Quantum Espresso it's a brand new calculation. There's going to be a point in your project, I think, where this is going to be something different, where basically you give Quantum Espresso the terminal output from a previous run as the initial conditions for a new run. And so that will be obvious when you see your project. But from scratch, this means it's a brand new run. We're not going to import any data. Prefix, H2 declares the file name prefix for all temporary files. So as we talked about, Quantum Espresso generates this directory and spits out like wave functions and all of this other information about your run. And so we just want to prefix all of those files with H2 to let us know that this belongs to the H2 run. So of course that can be anything. T-stress and T-PRN-FOR are just flags which says, okay, Quantum Espresso, I want you to compute the stress tensor and I want you to compute the forces. If you don't care about those things, you can set those equal to false. But as we talked about, we're ultimately going to try and find where the forces become zero on the ions, and so we do want to know about the forces. And so let's have it compute that for us. Pseudodir is where you store your pseudopotentials, and so the vanilla install of Quantum Espresso as it comes down and you install the package just directly from the internet, has a pseudopotential directory that's sort of located close to the bin directory. It's basically you just go one up from the bin, and then you go sudo, and that's where your pseudopotentials live. It turns out when you do your homework, your project, you're actually going to download a pseudopotential from the internet, and you're probably going to store it in your home directory or on your desktop somewhere, and so you're going to have to tell Quantum Espresso where that lives, and so you'll have to change this line to be the directory where you're holding your new pseudopotential that you downloaded from the internet, from NIST actually. But right now this is fine, so we don't need to change that right now. You will need to change it in your project. Okay, so you can also set an environment variable, Espresso sudo, that tells Quantum Espresso where the pseudopotential directory is, but it's easier just to change it in the input file. So I'd recommend you just change it directly in the input file if you need to do that. Okay, so this one is important. So line 8, outdir. And so Quantum Espresso spits out a bunch of junk, a bunch of sort of calculations and sort of runtime variables and iteration variables. That's how well it's converging. And for large systems, those can actually take up a huge amount of space. And so if you're running on your EWS system and you have a bunch of sort of homework files and projects from the last 4 years as a student here, you might not have enough space to accommodate all those files. And so what we actually want to do is give Quantum Espresso some sort of like sandbox space where it can dump all the files it wants, and we don't really care about it. And so it turns out that the engineering IT services have provided this volume called /temp/your username, and you may or may not have ever heard of this before, but basically it's sort of a scratch space where you can just dump files. There's sort of lots of file space. The problem is that it's not for long-term storage because periodically it will fill up, and then engineering IT will come along and just wipe all the data from that partition. And so it's fine for sort of short-term storage for dumping the output of a run, but it's no good for long-term storage. So for short-term, you can use /temp/your username. For long-term storage, for anything you don't want to get wiped every sort of Sunday night when engineering IT come and clean this partition, needs to be in sort of /home/your username, which is your standard home directory, which we've been accessing using tilde. Okay, so in the input file for Quantum Espresso, we want to tell it about this thing and allow it to use it. And so right now, what I have in your input file is /temp/$user, and so you should change $user to your own username. So let's everybody do that right now. So let's, however you're visualizing this file, close it down, reopen it in VI, and let's go and delete $user and change it to your username. So for me, that would be ALF. Okay, so let's take a second to do that. It should automatically create it when you need it. So if you've never used it before, it might not exist. And as soon as you start to write to it, it should appear. So you can test that. So you could just like echo some word, hello world, to the terminal and direct the output to /temp/your username /dumpfiles.txt and see if that appears. So that'd be a nice way to test it. Okay, so has everybody managed to modify that? Anybody having problems? Okay, so let's keep going. So at the risk of boring you, please do not store any of your projects or any long-term data there. It will be wiped and there will be no way to recover it. So don't use it for storage, only use it for dumping the output of runs. Okay. Okay, so that's the end of that block. So the next block is the system block. So you can continue to visualize your file in VI, or you can use LESS or text editor again, whatever you want to do. So down to lines 10 to 13, system block. So Brav is just the Brave's lattice. So it turns out it doesn't really matter because we're looking at a molecule. It does matter when you're looking at a crystal. And so when you do your project, it's going to be aluminum, and we need to make sure we have the right lattice structure for aluminum. But right now, we're just going to pick the simplest one, which is a simple cubic structure, because it doesn't matter, because we're looking at just 2 protons. So this is sort of irrelevant right now. Okay, then we're setting the dimensions of the cell. And so that's the fundamental unit cell that we're going to do all of our self-consistent field calculations in. And so we're going to set this to be, so can anyone tell me what the value of cell DM is in their file? 10? Okay, so that's 10 watts. What's the unit? Bohrs, that's right. Quantum Espresso uses bohrs. So 1 Bohr is about half an angstrom. And so it turns out this thing is about 5 angstrom cell. So it's a pretty big cell. So remembering back to what I said at the end of the lecture last time, why would we want to simulate the hydrogen molecule, which is really tiny, inside a giant real space cell? That's right. And so if we remember, we said that a lot of the calculations happen in reciprocal space. And when we have a giant real space cell, it means we have a tiny reciprocal space cell. And so that means that we can get away with using very, very few K points. Does that ring a bell to everybody? People remember this? So a real space cell being very big, reciprocal distances are the reciprocal of real space distances. So reciprocal distances are really small, and that's the reciprocal space is where we do our K point sampling. So if that is really small, we might only be able to use 1, 2, 3, or 4 K points. So it's a cheat when you're looking at molecular systems to use a giant real space cell so you can get away with a tiny reciprocal space cell. So if that doesn't make sense to you, if you sort of forgot about it, take a look at the lecture notes from at the end of last time, or you can ask me after class. But that's the reason we're looking at a really big cell there. Okay, then we've got the number of atoms, so each individual unique atom type, and the number of types of atoms. Okay, so just setting up our system, telling Quantum Espresso what we're actually going to be simulating. Okay, so the next one, this is one of the other things we can mess with. We said the energy cutoff. And so this is going to be something that we will change. And so we remember that we said the energy cutoff basically specifies the energy of the highest frequency wave in our basis set. So we said if your energy cutoff is really low, it just means you're working with sort of very slowly varying sine waves of very low frequency, and you can't get very high resolution on your wave function. If your energy cutoff is very large, you expand your basis set, and you have lots of plane waves with very high frequencies. And so they're very energetic waves. And so that means your basis set got bigger, and so you can do a better job of resolving the electronic wave function. So why wouldn't we always just use the biggest basis set in the world that we could possibly tolerate? Well, because it becomes much, much more expensive to do the calculation. So we talked about before, an important part of a density functional theory calculation is convergence. So we need to convince ourselves and convince our readers, convince me and your project that your basis set is big enough such that your energies are converged, but you're not going so big that you're just burning CPU cycles for no reason. And so we'll see that as we go through here. Okay, and so that's the energy cutoff. So just leave it as it is for right now, but we're going to play with that a little bit later. Okay, so any questions so far on the input file? So pretty straightforward, I think. Okay, so electrons block. So the way that we're actually going to solve the self-consistent field equations requires some sort of specification of parameters. So it turns out you use a diagonalization method called David, I think, is written in your script. I don't know why it's called that, but it works well. It's the default. Mixing mode, don't worry about that. Convergence threshold, don't really worry about that. So it's how we're solving mechanically the self-consistent field equations. So typically we just stick with those defaults unless we have some good reason to use something different. Okay, so that's down to electrons. So let me zoom down a little further. So the very last block is atomic species. And so we told Quantum Espresso up here that we have 2 atoms of one type. So that's just start telling Quantum Espresso what to expect. And then we get down here and we actually tell Quantum Espresso what we have. And so down here we have atomic positions, and it's going to be atomic symbol, and then X, Y, and Z. So the species, hydrogen, this is its mass, this is the pseudopotential we want to use, and the atomic positions for hydrogen number 1 is living at coordinates x, y, and z in Bohr, negative 0.7 in the x direction, 0, 0 in y and z, and the other H is at 0.7 Bohr in the x direction, 0, 0 in y and z. So pretty simple. Any questions about that? So do you think it would matter if you set your system up as we have it here, which is basically one hydrogen atom 0.7 to the left of the origin, one hydrogen atom 0.7 to the right of the origin along the x-axis, or if you set it up with them along the z or along the y or along some diagonal, do you think you should get different answers? No, of course not. So it doesn't matter. So we're just take the simplest one, which is to lie them along the x-axis. So you can do whatever you like. Okay, and then the final command here is the k-point sampling, and so we tell it to do k-point, start setting up the k-point grid automatically, but we tell it where we want the k-point. So down here is the line 111000, and so this says the number of intervals in the particular direction, so x, y, and z, and the offset of the grid in x, y, and z. So it's basically telling Quantum Espresso how dense you want your grid to be, and then whether you want your grid to be offset. So typically we don't usually offset our grid unless we have a good reason to, but the important part is right here, which says how dense you want your grid in x, y, and z. And so right now we've said we just want one sort of lattice grid in x, one in y, one in z, which basically boils down to a single k-point. And this is exactly what we were talking about before, that we have a giant real space cell, so we have a tiny reciprocal space cell, and we can get away with just one k-point. So when you do your project for aluminum, that will not be the case, and you'll need to worry about how densely you sample your k-point space. But for right now, we don't care. We just sample a single point. Okay, so any questions about the file? Yes? Yes, that's a good question. Actually, at the end of this walkthrough, there's a bunch of sort of questions and answers. And one of the questions is, would you ever want a non-uniform k-point grid? And the answer is, sometimes in some very special cases you might. If you know the energy is very rapidly varying in a particular region of reciprocal space, you might populate that more densely and then populate the rest of it more sparsely so you can get some CPU savings. So if you have sort of prior knowledge about the system, and you're really worried about CPU time, you might do a smarter k-point grid. So yeah, great question. Simplest thing is just to, if you're not worried about CPU cycles, just to dump down a uniform grid. Okay. All right, so that was setting up our input file. And so let's proceed. Okay, so then let's look up and open in less or in your text editor the other file we downloaded, so h2.relax.int. And so it turns out that this file is basically identical to your h2.scf.imp file, apart from two differences. And so it turns out that you're doing a calculation, instead of calculation equals SCF, which is a self-consistent field calculation, you're doing a relaxation calculation. And so that's exactly what Michael said earlier, that you take the first derivative of the energy with respect to the bond length, and so you sort of iteratively solve until you hit the bottom of your energy well. And so you solve until the forces on the ions are zero. And that's known as a relaxation calculation. So that's really nice because Quantum Espresso is going to do it all for us. We just have to tell it to do it by giving it the relax command. And then it turns out when you give it the relax command, you also need an extra block of code, which is ions. And it turns out that you just open the blocks, then immediately close it, and accept all the default values for any of the parameters that might live in there. If you're interested as to what actually lives in the ions block or in any of the other blocks, you can, of course, look up the Quantum Espresso documentation. But just take my word for it for now that we're just taking all the default parameters in here, and it's going to run just fine. Okay, any questions on the input files? Yeah. So if you have just this, it's going to dump it to the directory in which your terminal exists when you make the call. So if you're on your desktop and you make this call, it's going to dump this file to the desktop. Of course, you can make it write to wherever you want. And so you could set this to sort of /home/ your username /QE/H2/ and then the file name h2.sts.out. And so this is just standard bash. And so you can redirect this to wherever you want. So if you don't preface it with any path, it's just going to dump it into the current working directory, but you can send it to wherever you like. Similarly, you could source this file from wherever you like. If you're in your present working directory, it doesn't actually contain this file, but it's located somewhere else, you could just put some path in front of this and source the input file from some remote location. It might even be on a different server entirely. That's absolutely fine. Yes, great question. Any other questions? Okay, so this is a big moment. We're actually going to do a calculation. So let's do the calculation together. Okay, so as we said, we're now going to run the code, and we do not need any of this stuff out the front because it's stored nicely in our path that we modified at the beginning of class. And so all you're going to need is pw.x and then the rest of this line here, the input file and the output file. So let's do that and see if it works. Okay, so did everyone manage to get it to run? Let me make this text a little bigger. Okay, did anyone not manage to get it to run? Did anyone get some error when they typed this in? Okay, terrific. Congratulations, you're all computational materials scientists now. You've actually done a DFT calculation. Okay, so this is sort of the fundamental tension in computational materials science. It's super easy just to modify an input file and run the code. You could have done this without me presenting to you any of the theory of quantum mechanics. The problem is you don't know what you're doing and you don't know what you're calculating. So that's why we went through all the pain of the theory and the praxis, so you have some feeling for what we're actually modifying underneath. But if you're just interested in sort of the practicality of running code is really easy. All of sort of the scientific important questions and answers come from actually understanding the theory that underpins the code, which is sort of why we went through all that stuff. So I hope now you will forgive me for sort of putting you through all those terrible lectures, and now you've actually seen how easy it is to run the code. Let's see what the answers look like and try and interpret them within the perspective of now understanding some of the quantum mechanical theory. Okay, so let's look up our output file. So in the same way as you visualize your input files, just do a less or do a text editor to open up the output file, and let's take a look through the output. Okay, so at the top here, there's just sort of a bunch of references and telling you some information about the code. It's a serial version. If I compiled it differently, I could have compiled the parallel version, which would run over multiple CPU cores. But we're just using the serial version right now. It's reading input, and so the input it gets was from that file, and so we sent it this input and told it to do a calculation for us. So if we just sort of scroll down through the file, so hitting spacebar and left will take you down. It just gives you some information about all of the way that you've set up the run. And so you can see here that we're studying hydrogen. We're using the PBE exchange correlation, which is sort of the default one. So we didn't describe that in the input file, but we're accepting the default exchange correlation functional. As you study aluminum, I think you will have the opportunity to change your exchange correlation functional. Then you will change all four things: exchange correlation functional, pseudopotential, energy cutoff, and K-point sampling. And so we're doing 3 of them right now. The only one that we didn't change was the exchange correlation functional. Okay, and so let's scroll down a little further. So there's a bunch of stuff that just tells you about the setup of your system, the dimensions of your cell, so it's 10 bore by 10 bore by 10 bore, all of the input stuff you told Quantum Espresso. Let's keep going. So a bunch of information. It's using an ultra-soft pseudopotential from Vanderbilt. Setup of the system, and so we can see where ions live, a negative 0.07 and 0.07 in lattice units. So the lattice is 10, and so this is why it's 10-fold smaller than actually what we told it, which is 0.7 Bohr, because this is not in Bohr, this is in lattice units. Okay, then some sort of CPU information for how intensive this run was, and so it was all requiring only fractions of megabytes, since this is a very small run, but you will need to worry about this when you're studying very big systems, so you can max out the RAM on your computer, and then you really hit some problems, you're going to have to start using parallel clusters, etc. But right now, we're sort of happy to do this on a serial machine. Okay, then you can come through and you can see all of the energy calculations, and then right down at the bottom, once it's actually converged, there's a bunch of iterations. So you can see we're now at iteration number 4, iteration number 5. So what are we iterating on? So what is being iterated on? What are we trying to converge? Why can't we just do it in a single shot? Why do we have to iteratively solve? Yeah. So right now this is just pinning the ions. So there's no sort of bond length being searched over, because this is the SDF code, not the relax code. So what is being iterated upon? That's right, and so the self-consistent field energy. We said that you have to guess some initial distribution for your electrons. You have to guess an electron density, and then you have to resolve for that electron density self-consistently. So we make some guess for it. It may be wrong. We get some energy, and that sort of gives us our next update for the electronic density. And so it's because the density appears on both sides of our equation, we have to solve for it self-consistently. And so if you go back and look at the slides, you'll see that. And so we make a guess for the wave functions, for the density. We then update that guess and cycle around until it converges. And so as soon as the density converges, the energy will also have converged. And so we need to make sure our calculation is converged. That's why it's self-consistent. Okay, so that's important. It's not a single shot calculation. We need to iteratively solve. So as you come through, you will see the estimated accuracy and the self-consistent field energy. So we're down to sort of some very small fraction of a Rydberg, and so we're starting to converge the energy, and so we're getting there. And then by sort of iteration 6, it's below the tolerance. And so in your input file, you had that line that said convergence criterion, so the convergence energy. So once your estimated SDF accuracy is below your convergence threshold, the iterative solver will stop and say, okay, I've done a good enough job for what you need. So you'll see a line end of self-consistent calculation. It only took about 0.8 CPU seconds, so that's great. And then if you go down to the bottom here, this is very near the bottom of the file, this is the most important line. So the total self-consistent field energy for your system. So given that you have two protons that are pinned at these particular positions, so 0.7 Bohr on one side of the origin, 0.7 Bohr on the other side of the origin, when you relax the electrons around those protons, around that field, the imposed field by the ions, you get this energy. So this is really the calculation that we're trying to do. We're trying to calculate this energy. And so Quantum Espresso knows that this is probably the most important line that you care about, and so it prefixes the line with an exclamation point. And so why is that useful? Well, it turns out it makes it very easy to grep for the line. And so what do I mean by that? It means that you can do so you can latch the file and you can type it to grep and tell it to look for an exclamation point, and grep will spit out that line. So it means that you don't have to sort of scroll through the file and find this line. So we remember that this last command is just displaying the file. This is the pipe character that says take that output and give it to somebody else. And who are we going to give it to? We're going to give it to grep, which is that utility that just does a line-by-line search for a particular string. And the string we want to search for is an exclamation point. So any line that contains an exclamation point will be spat out by grep. And so it's a very sort of clean way of, finding your final energy. So you can imagine we could make this even more complicated, that we could pipe this somewhere else, that once we have this line, we could use awk to perhaps grab this energy and send it to MATLAB and make some plots and do all sorts of crazy stuff. So very sort of nice code that I use all the time for sort of finding lines in a file very efficiently. Okay, so let's open the file back up and scroll down to the bottom. Okay, so that was the line we were just at. That's the one that we grabbed out. And then the other important part is right here. And so each of the atoms is experiencing a non-zero net force. So this force obviously arises from the Coulombic repulsion between the two positively charged protons, but also from the equilibrated structure of the electron cloud. And so the electrons are acting like a glue between the protons. They're stopping them from just flying apart. If you had two bare protons, the equilibrium structure would be at infinity, and life wouldn't exist as we know it. The electrons allow protons to live close to one another and make molecules and crystals. So there's a non-zero net force. And so like we said before, this is because we've made a bad guess for our bond length. So one thing we could do is just run through and guess different bond lengths until these become zero, or we can do a little bit better and actually use the relax calculation within Quantum Espresso to automatically find the minimum energy, find where these guys zero out. Okay, so if you only look at two things in this file, it should be this line and sort of this little block here. That's the most important things that we've calculated. So is everybody okay with everything there? People have managed to generate this file. People understand most of the output of this file. Any questions about anything in there? Yeah. Okay, so that's a problem. So let's solve that problem. Okay, so what are you missing? So where is the, okay, so that needs to be, okay. Okay, so there are two problems. So let's change that back to your username. Okay, and then where is the walkthrough? So the text document with all the commands in it that we've been running through on the screen. So did you download that document? Okay, so let's open that. No, so the walkthrough. So let's just double click on that to open it in Microsoft Word. Okay, so let's go down to where it's saying how to execute the command. Yeah, the next page. Yeah, okay, so what are you missing? So there's a very important character missing in your call. Yeah, exactly. So that's it. So whenever you have a problem, usually it's because you've made a silly spelling mistake. And so yeah, that will solve it. Okay, is anyone else having difficulties running the code? Everybody's managed to generate the output file? Okay, terrific. So let's move on to the relax. Okay, so let's run the relax code. So it's going to be pw.x, and we're going to feed it this time h2.relax.imp, and we're going to output h2.relax.out. Okay, so this one is going to have sort of two iterative loops happening. You're going to have the iterative loop we just saw, where for a particular separation of the protons, you're going to self-consistently solve the Kohn-Sham equation and compute the energy. And then we're going to have a second iterative loop outside of that, which is iterating over the bond length. There are two iterations happening here. Does that make sense to everybody? So we've already done one of them in the self-consistent field calculation, but then we're going to supplement that with another one, which is figuring out what is going to be the equilibrium bond length. So this is going to take a little longer to run. I mean, not very long. It's a few seconds rather than less than 1 second. And you're going to see exactly what I've described in the output file. So has everybody managed to run that? Anyone having difficulty running that? Okay, if the first one ran, probably the second one will run. Was that one okay for you this time? Okay, terrific. So let's take a look at that file, the output file. Oh. Okay, so last h2.relax.out. Okay, so there's all this stuff at the top that we saw before, setting up the system. Then we're running through a series of SCF calculations. So you will get down to something like this, and you will see end of self-consistent calculation, and you will see some energy. So that's the first SCF calculation. That's the first round in the outer iterative loop. And then as you go down, you will see, okay, there's a net force on my ion. This is basically, this top part of your output file is basically the complete output we generated from h2.scs.imp. It's a single self-consistent field calculation for a particular separation of the protons. Relax now goes further. It now says, this is non-zero. I need to actually figure out how I'm going to change my bond length. So the left-hand atom is being pushed out to the left, and the right-hand atom is being pushed out to the right. And so Relax is going to say, well, let me take a step, and let me make the bond length a little bit bigger, and see if I can make these forces a little bit smaller. And so as we run down, you'll see it's going to enter another self-consistent field calculation at a different bond length. So if we push down here, you can see that this bond length has increased. And so the Relax code has stepped the bond length to be a little bit bigger, and it's going to do a brand new SCF calculation and see if the forces have zeroed out yet. So obviously it does this in an intelligent manner. It uses, I guess, some variant of conjugate gradient descent. It could use steepest descent if you tell it to do that. But so this is not just arbitrary. It's not just guessing. It's actually doing some sort of Newton searching in order to get the bond length equilibrated as efficiently as possible. Okay, so it's going to happen a bunch of times. And so you can scroll down the file and see a series of sequential SCF calculations. And the bond length will change as a function of time as you go through this calculation. And then down at the very bottom, once you've hit your terminal criteria, you will see sort of the final bond length. And so this is the terminal bond length after the outer iterative loop has converged to within the tolerance you told it. Okay, so does that make sense to everybody? Any questions about that? Okay, so if you do a same grep call on this file, so let's pipe it to grep exclamation point. Now you will see a sort of bunch of energies because each one corresponds to a separate SCF calculation. So that was the first one with our initial guess, gets better, gets better, gets better, and at this point we've converged to within the tolerance in energy that we specified in our input file. If you change that convergence criterion to be more and more restrictive, you'll get more and more SCF iterations, and it will take longer and longer for your code to run. Okay. Then you can also run through the code and see how the atom positions are changing in each calculation. And you'll see that they're sort of moving towards some equilibrium bond length. Okay, and so what is the bond length in Bohr's? So it's going to be sort of absolute value of this guy plus the absolute value of this guy. So it's going to be something like 1.44 Bohr. And so let's change that into angstroms or picometers, and then let's just use Google to figure out what the bond length of a hydrogen molecule is and see how well we did. So why don't you just take a second to do that? So take this output, you've computed something beautiful, so let's actually compare it to experiment. Convert Bohr into picometers or angstroms, and then just use Google to look up the NIST chemistry webbook or Wikipedia or whatever your favorite site is to find out the bond length of a hydrogen atom, hydrogen molecule, and see how well we did. So does anyone have an answer yet? Yeah. 38 picometers. So, and what is the experimental value? 53. Okay. Anyone else got any answers? Yep. For your DFT result or for your experimental value? For your result, okay. And what was the experimental value? 74. Okay. Anyone else? How about in the back row over there? Anyone calculate the DFT result up there? 38? Okay, so there's something suspicious happening because 38 is approximately half of 76. So who's right and who's wrong? Yep. That's right. So you're probably going to get 38 picometers here, but there's also 38 picometers here. So you need to make sure you're taking the whole bond length and not just the distance from the origin of one proton. So you should be getting around. So DFT and our DFT should be approximately 76 picometers, and from experiment, it's around 74 picometers. So that should be sort of the ballpark of what you're seeing, depending on what source you look up and depending on the particular convergence of your calculation. But this is kind of remarkable. So the first time I did this, I was like, this is sort of amazing. So without any free parameters beyond sort of the approximations that we're forced to make in DFT, we're able to compute how far apart the protons should be in a molecule. And compared to experiment, you get it within sort of 1% or less, sort of a fraction of a percent, which is sort of spectacular. And so, of course, for more complex systems, we don't do as well, but it's sort of remarkable that we can do this so easily just on a workstation in front of us using a relatively simple code and solving relatively complex equations and solving them really, really quickly. So I think it's sort of a very exciting thing the first time that you do it, or at least it was for nerds like me. So I thought that was neat. Okay, so I think that'll do it for today. And so next time we're going to worry about convergence in energy cutoff. So we said if you're making a reasonable calculation, you need to show it's converged. Turns out we're pretty close to converge, but we need to prove that to ourselves. And we're not going to do any k-point convergence because of our trick with a tiny, tiny reciprocal space. But in your project, you will do k-point convergence. So typically, you always have to do two kinds of convergence. Here, we're only going to worry about one. Okay, so that'll do it. If you have any questions, please come talk to me. If you're interested in the CSE program, either as an undergraduate or a graduate certificate, do go to this website, take a look. I can probably answer some of your questions or point you to one of the program administrators if you're really interested in signing up for that. All right, so thanks, folks. See you next time.